So this section is 2.2. It's on functions. And you're probably familiar with these. You've probably seen these before. So we're going to run through the basics again, make sure we're all on the same page, all understand what we're looking for here. So here's how we're going to describe a function. A function is a very consistent mathematical rule that takes whatever number or expression. It's possible to plug in either a number or an expression. It gets a little weird sometimes. Okay? It does some math on it, for lack of a better way of describing it, and then it gives you an answer. So we dump something in, and it spits out an answer. Okay? It works the same way every time you plug something in. Okay? So let's see, there's a blank here. The blank is the set of numbers you plug in. Anybody know what name we give those things? The other one starts with a D. Very good, okay? So we call the domain, that's the set of things that you can plug into a function. So if we've got this mathematical rule, anything that's okay to plug in, we call the domain, and any number, anything that you can plug in, we call that the range. Okay, so domain and range. Okay, most of the time we plug in x's and get out y's. So usually the domain are the x's and the range are the y's. Now it's possible to deal with different things where they're not x's and y's, and then we go back to the original definition. The domain are the things you plug in, the range are the things that you get out. Okay? Now you may or may not be familiar with this notation. This is called function notation. So function notation right here. So function notation looks like this. And the way we read this is we literally say the words f of x. So say the letter f, the word of, and the letter x. So f of x. F of x is the same as y, so we could say y is equal to f of x. And we'll talk about why function notation is nice as we go through and discuss this. So, let's see. First example, is f of x equals x minus 3, is that a function? So you normally saw it written like this, y equals x minus 3. Remember, y is the same as f of x, so you could write it either way. So the first question is this a function? And we're just going to think about this for just a second. So it has to be a really consistent mathematical rule. That when you put a number in, it does some math on it, and it spits out the same number. So let's plug in a negative 2. If you plug in a negative 2, you put it right here. So it's x minus 3. So this would be negative 2 minus 3. What's our answer on that one? Negative 5. So when you plug in a negative 2, you get out a negative 5. Now here's what we mean by consistent. Let's say I teach the same class later today, and in that class we plug in a negative 2 and we get out a 14. Would that be a function? No. We want it to be consistent. On this rule, every time we plug in a negative 2, what is this function going to spit out? It's going to spit out a negative 5. So this looks like this is going to be a yes here. When we plug in a negative 1, negative 1 minus 3, so this would be a negative 4. Nice colors here. Oops, didn't get that changed. There we go. If we plugged in a 0 and we subtract 3, we're going to get a negative 3. And what happens if we plug in a 3? We get out a 0. Now this one's a little bit interesting. This next one, remember, we said you could plug in a number or an expression. Let's plug in an a. So if I plug an a into this, what do I get? You get a minus 3. Okay? Which kind of matches up with our little pattern here. Whatever I plug in, this one is 3 less. Always 3 less, 3 less, 3 less. If I plug in an a, what's going to come out is 3 less than a minus 3. Okay? So sometimes we describe functions as machines. We dump things in, it does some math on it, and then it spits out whatever the function value is. So we dump in x's, we get out f of x's. Dump in x's, we get out y's. Y's are the equivalent of x's, or y's are the equivalent of f of x's. Okay? So there are a couple other ways to describe a function. Here's one other way. Each member of the domain corresponds with exactly one member of the range. So there's this, like we call it a one-to-one correspondence. So that one corresponds to that one, and that one, and that one, and so forth. Okay? Or if we set it in terms of x's and y's, each x corresponds with only one y. So each x can correspond with only one y. That's the direction that it goes. So we don't always have to deal with numbers when we're talking about functions. It's possible to deal with words and phrases and different things like that. So let's say our function is the birthplaces of all students in Math 1010. So our domain would be students in Math 1010. Our range would be dates or birth dates. Oh, these are birthplaces. Birthplaces, I'm sorry. Okay? So the domain is going to be students or their names, and the range is going to be places. So let's take a couple people in here. Well, let's see. We've got a couple Sarahs and a couple Amelias, so we'll go with a McKay. I think there's only one McKay. Did I spell that right?
Yeah.
Okay. We've got a Taylor. Okay. And we've got an Emily over here. All right. And we've got Susie. Did I spell that right? Okay. All right. So now over here, I'm going to write down, let's see, McKay, where were you born?
Provo.
Provo. Okay. Taylor, where were you born?
Tyler.
Oh, Tyler. Sorry, Tyler. Sandy. Emily. West Jordan. And Susie. Nigeria. Okay. Now, here's what we mean when we say every element in the domain corresponds with one element in the range. It means McKay was born in Provo. He corresponds with Provo. Tyler corresponds with Sandy. Emily corresponds with West Jordan. And Susie corresponds with Nigeria. See this one direction correspondence here? Okay, now, is anybody else here born in Sandy or West Jordan? Okay, Amelia, we'll put her down. Where were you born? She was born in West Jordan. Okay, is that still a function? Okay, now think about this for just a second. It says each member of the domain corresponds with only one member of the range. So does each person over here have only one line going to a city over here? Okay, so this is a function. Okay, that is a function. Now, here's where we could make it break down. Let's say McKay, we draw a line like this. Okay, now in your gut, there's something wrong with that, isn't there?
Yeah.
Okay, McKay was born in Provo and he was born in Nigeria. Now you're not broken in pieces, are you? Okay, so there's something wrong with that. That's that consistent part. We don't want to ask McKay on Friday, hey McKay, where were you born? And he says Provo. And we come back on Monday and say, McKay, where were you born? And he says Nigeria. Okay? There's only one answer for each number that you plug in or each person that we plug into this. Does that make sense? Okay, you can kind of feel that there's something wrong with that. Okay? So the answer to this one is yes, that was a function. Okay, now let's go back to looking at numbers. So on this one right here, you can also represent, in addition to just talking about words or using formulas, we could represent it with sets of numbers. So here's an XY pair, -4, 3, 0, 4, 1, -1, 2, 1, and 3, 3. So let's write down what the domain is. The domain is -4, 0, 1, 2, and 3. Okay, now let's look at the range. The range is 3 from this guy right here, 4 from this one right here, -1, 1, and 3 again. Now, do I need to write another 3? I don't, okay? Okay, now let's do this. Okay, we can call this a map. We can map one to the other. Let's draw these lines here. -4 corresponds to 3. 0 corresponds to 4. 1 corresponds to -1. 2 corresponds to 1. And where do I draw the line here? 3 corresponds to what? Back up to right here. Now, is this still a function? It is, because each member of the domain corresponds to only one thing in the range. We didn't go the other way. Okay, that'll come down the road. Okay, we can add a restriction to this. We usually do that in 10, well, let's see, toward the end of this class we'll actually do that. Okay? Now, we can also write down what the domain is. The domain is the set of numbers that are the first elements, or the set of x's. So that's -4, 0, 1, 2, and 3. There's the domain and the range. Sorry, my set brackets look pretty ugly. Okay, they should look like this. Everybody watching, I'm only going to do this once. Here's a really nice set bracket. Okay? And we've got a 3, we've got a 4, a -1, a 1, and we already said we don't have to rewrite that 3 because it's already represented there. Okay? All right. So that is a function. Now, everybody watching? What if I added this number? 1, 2. I've already got a 1 in the domain. If I added a 2 here, here's what happens. So to save time, I'm going to put this right here. Okay, because this would produce the same thing. Where do I have to draw a line now? If I add this one right here, I've got to draw a line from the 1 over here to the 2. Now, is that okay? Is that a function? Okay, the answer there is nope, it's not. For the same reason, for the same little gut level intuition that, well, we can't have a 1 corresponding to a -1 and to a 2, just like we couldn't have McKay born in 2 places. Okay? All right. Any questions? Okay, now, there's another way that you can tell this by looking at the graph. We haven't looked at many graphs today. Let's take a look at this one right here. We can see that problem on a graph. So let's graph these points. -4, 3, so back 4 and up 3. So we're right there. 0, 4, we're right there. 1, -1, right here. 2, 1, right here. And 3, 3, we're right here. Now, everything is okay to this point. Which one screwed it up? That 1, 2. Let's come back here and let's draw where that 1, 2 is. It's right here. So here's the problem. The problem is, if I go to -4, I know my answer's 3. If I go to 0, I know my answer's 4. If I go to 3, I know it's 3. If I go to 2, I know the answer is 1. The y that corresponds to that x value is a 1. But what if I go to 1? What's the answer? Is it -1 or is it, or is it 2? That's the problem. The problem is right here. These two numbers are on the same vertical line. So that gives us a way to check whether or not a graph comes from a function. We don't have to check all the points doing the stuff that we were doing here. Gosh, does each one of them correspond? We can just look at it and say, well, let's see. Do we have this problem of 2 points being stacked on top of each other on the same vertical line? So if I run through here and I draw a bunch of vertical lines, how many times does it hit that little curved graph? Only once. Every single one of them hit only once. So this one is a yes. What about this one right here? Nope. There's a point where it hits it twice, so the answer here is no. How about this one? Okay, where is the problem, Amelia? It's right here, isn't it? Okay? Because if I draw this line, it only hits once. Okay, everybody watching, please? This is a little detail here. How many places does this hit the graph? One here. This is an open circle, so there's not a point there. So there's no problem there. Is there a problem here? Nope, because both of these are open circles. Same thing here. Here's the problem right there. This is the big problem. Hits there, and then it hits again. So the answer on this one is no, that's not a function. Okay? That graph could not have come from a function, a consistent rule, because those 2 points are right on top of each other. If we went to this x value, we wouldn't know whether we're supposed to go up or down. So we can use that. We can sketch something that's a function and something that's not a function. So draw a function right here and draw something that's not a function right there. Don't just copy the ones above. Simple line. Is that a function? Yep, because every vertical line would only intersect at once. What about some graphs that you might be a little more familiar with? What about something that's this shape? That would be a function. Okay, something that does this. Anything that doesn't go back on itself is a function. On the other hand, if we have something that does this, can't be a function because right here, these points are stacked on top of themselves. Anything that goes back on itself would not be a function. So anything like that, not a function. Okay? All right, any questions? Sure? Okay, let's take a look at problem number 56. This is out of the textbook. You have one very similar to it on your Math Excel assignment. And by the way, today is just Math Excel again, right? Just the homework on Math Excel and then the quiz. Oh, and before I forget, had somebody ask me a question. If you have to draw a line, so when you were doing the orientation, you know how had you draw some lines, I think. When you do those, a couple things. If you don't do the exact points that they have in the answer, for some reason it marks it wrong. Okay, so do a, help me solve this or show me an example. Try and put the points right where they do. The other thing is occasionally they'll have you do some shading, like you'll draw a line, you'll shade one side or the other. The bucket that dumps the paint in the shaded area, you have to leave that in the shaded area. You can't put it outside. Okay, so just remember there's some little quirky things about the program, but overall it's pretty darn cool. Okay, so you've got some problems that are like this. This is not f of x. What would we call this? H of x. So it just means we're going to plug in wherever there's an x, we're going to put a 4. So this would be 5 times 4 minus 1. The answer is 19. Now, that literally means h of 4 is 19. So here's what I like about function notation. One, it's used all the time, so we've got to get familiar with it. And two is this. Remember we said h of x is the same as y? Well, this right here is the x value, and this right here is the y value. So that's the point that you're going to graph. If it said graph it, we'd graph the point 4, 19. If we did h of negative 3, 5 times negative 3, minus 1, so that's going to be negative 16. Again, if h of negative 3, if h of negative 3 is negative 16, the point that that would correspond to would be negative 3, negative 16. Okay, that would be the point that we'd graph. Okay, you don't have to do that on every one. I'm just trying to point out. This is your answer right here, 19, negative 16. Next one, h of a. 5 times a minus 1, so what would that be? 5a minus 1. It's possible to have an expression rather than a number for an answer. Go ahead and do this one. When it was a 4, we plugged in a 4. When it was a negative 3, we plugged in a negative 3. When it was an a, we plugged in an a. So we're literally going to plug in an a plus 1. So 5 times a plus 1 minus 1. So that's going to be 5a plus 5 minus 1. So what's the answer on this? 5a plus 4. Again, a different expression, but that is the answer. And then let's take a look at this next one here. This is going to be h of a plus 3. So it comes in this piece, and then we add this piece right here. So h of a is what we get when we plug in an a. There's the h of a. Then we're going to add 3. So what's the final answer? 5a plus 2 is the final answer. Okay? All right. Any questions? Okay. Before we do problem 62, and we're just about done with this, I want to take a look at this right here. For some reason, this messes people up, and I want you to keep this straight. Some people think you can do both of these problems. Some people think you can do neither of these problems. Okay? Those are both wrong. Okay? You can only do one of these. Okay? This one right here is the one that you can do. You cannot divide by 0. And the way I like to explain this is this way. Let's say you had this many people together and you wanted to give them some pizza. So let's say I had no pizza and I wanted to give some to 7 people. How much would each one of them get? They'd get nothing. They'd get 0. Okay? No pizza to divide? Who cares if you've got 7 people around? You can't give them any pizza or cookies or candy or whatever you want to do. Okay? On this one right here. So this was pizzas and this was people. Each one of them got nothing. How many pizzas do we have here? We got 2 pizzas. How many people? Okay, so if I want to take 2 pizzas and divide it among 0 people, how many do each of them get? Okay, do you see what the problem is there? Do you see how that's a different question? That's a dumb question to even ask. There aren't even any people to give pizza to. Okay? So we say this is, what was the word again, Amelia? We call this undefined. You cannot divide by 0. Taking 0 and dividing it up, that's okay. You still have 0. If you had 0 to start with and divide it up, you've still got 0. If you try and divide by 0, take 2 and divide it into 0 pieces, doesn't work. Okay? So, you cannot divide by 0. And we're going to mention that over and over again. If you have division in a problem, you have to be careful, especially if it's an algebraic expression. So on this one, they say, find the domain of the following. Now, normally you can plug in any number you want. So if we look at this problem that we did earlier, that one right there, you can pick any number you want, plug it in and subtract 3 from it. It will give you an answer. Let's take a look at this guy right here, though. Can you plug in any number you want on this one? You can't plug in 6. Because if you try and plug in 6, you get 7 over 6 minus 6 is 7 divided by 0, and we know that's not okay. Okay? You can't divide by 0. So what that means is 6 isn't in the domain, so this is what we do. Take 6 minus x, set it equal to 0, because that's the only thing the denominator cannot be. Okay? That's the one number that we can't plug in, so all we do is we say that can't equal 6. Okay? So what we could say here is, this book uses something called set builder notation. We could say all reals, as long as they're not equal to 6. Or we could say the set of x's such that x is not equal to 6. Okay? Now, either one of these is acceptable. That one's just fine, and that one's just fine. Okay? That's called set builder notation. Okay? Either one of those is okay. Let's take a look at this one right here. What number can we not plug into this? 3. You can't plug in a 3. So if you just want to write x not equal to 3, that would be just fine. If you want to write all reals except for this, that would be fine. If you wanted to do set builder notation and write x such that x is not equal to 3, that would be okay too. Now, I do want to show you that you can solve it using this. You could say x minus 3 cannot equal 0. Get the same answer that way too. Okay. Any questions? Okay, let's look at the next example. Let's see, what's the domain of this one? Is there anything that we cannot plug in there? Can you plug in 5? Negative 3? What about 0? Can you plug 0 in? Yep. Any positive number is okay, right? Any negative numbers okay. And 0 is okay. So this would be all reals. Okay. Or again, you can answer with that script R. That's it. Again, this function doesn't have any what I call domain issues. It doesn't have anything weird going on like division. If it's got division in it, you have to be careful. And then later on in the semester, we're going to learn other things that you've got to be careful with. Okay? All right. So let's take a look at a graph and let's figure out what the domain and range is. I like to describe this way. Finding the domain and the range on a graph is very easy if you use what we call the squish technique. Okay? So if you want to find the domain, take the graph and squish it on the x-axis. So see this blue graph right here? We're going to take all the points and slide them up here, all the points and slide them here. Okay? So it's kind of like taking the graph and just squishing it onto the x-axis. So all of these points would come down here, all of these points would come up here. So what part of the x-axis would be covered? It would be covered from here all the way to there, right? So let's write down what that is. And we usually write this down in what we call interval notation. So this starts at -2. Where does it end? Ends at +4. So the domain would be this. It would start at -2, put a comma, and then put a 4. So write down where we start, write down where we stop, and then we put either parentheses or square brackets around the endpoints to say whether or not they're included. Okay, is the -2, is it included? Is that an open or a closed endpoint? Open. So we use round brackets to indicate that it's not included. And then is the 4 included? Yeah, so we put this on there. You with me? Okay. We can also write it like this. And this textbook in Math Excel will want you to write it in set builder notation a lot. So we'd write the set of x's. That's a set bracket. I'm saying the set of x's. This bar means such that x is less than or equal to 4, greater than -2. Okay, that's how you'd write that. Good? Okay. Let's do the range and we're done. Okay, so if you find the domain by squishing things on the x-axis, how do you find the range? Squish it on the y. So that would mean all these points would come over here, all those points would come over here, those points would come over here. So we start down here at, let's see, where is this? -3, and where do we stop? Stop at 1. So the range is, where do we start? And again, you always start toward the negative. Start down here at -infinity. Where do we start? -3, comma, where do we stop? 1. Now, this one's easy. Square around the 1. Square. Square or round around the -3. Square. Because it does that, it actually touches -3, right? So square there. Okay? If we wrote it in set builder notation, y such that y is between 1 and -3, and these would be less than or equal to. So this is called interval notation. This is called set builder notation. Okay? All right. Are there any questions? Yeah.
So which ones we use for Math Excel?
It'll show you. Yeah. A lot of times it'll have the set started, and it might even have the X in the bar there. Okay. If not, it'll give you the tools to build that. Okay. Or it'll say write it in interval notation. Okay. So interval notation here, and set builder notation here. Okay. Good question. Anything else? Okay. How many of you brought? Let's see. Did anybody bring a laptop today? All right, very good. We got quite a few. We'll probably have enough computers in here to go ahead and hop on. So we've got 15 minutes. That may be enough time to get done. Wouldn't that be a good weekend? Okay. Remember, Monday when you walk in, you're going to want to be done with 1.3, 2.1, and 2.2. If you've got any questions that you didn't want to ask in front of everybody else, make sure you ask them now.